Okay. Let's get going. Any questions before we get started? All right. If not, then we'll just keep going with our history of convolutional neural networks via the Imagenet competition. Last time we talked about AlexNet, got into the details of the architecture and how it was trained. We learned about data augmentation, we learned about dropout and some other techniques for how this was trained and how it allowed to perform so well. Okay, so we're going to kind of move through year by year here. 2013, there really is not a whole lot that happens here other than just some improvements with respect to hyperparameters. So, we have a little bit better hardware. We have a little bit more time to search the hyperparameter space. It's basically the same architecture, just better hyperparameters. It looks like, so here are some of the changes. We changed the first convolutional layer. So instead of it being an 11 by 11 filter with stride 4, we go to a 7 by 7 with stride 2. And then we just add a whole bunch of filters. So at these different convolutional layers, we increase it by a whole bunch more, right? 384 to 512, 384 to 1024, 256 to 512. So more memory in GPUs allows us to have a bigger model. This helped quite a bit. And we go from 16.4% to 11.7%. So just those small, I mean, I don't know if they're small, but just those few changes really gave, again, a huge increase in the accuracy or decrease in the error rate. So that's great. Low-hanging fruit, for sure. Then we get to 2014. In 2014, there are two models that we're going to look at. One of them won, this Google Net, or what we actually now call Inception Net. And so that one actually won, but there was another convolutional network that was close. And it's called BGG for certain reasons, and the two architectures are quite different from each other. Actually, very, very different. We're going to go through them right now. BGG is really kind of like a simplification of the ideas of like, what is a convolutional neural network? What should it look like? What are the building blocks of a convolutional network? And Google Net here, Inception, totally goes like the opposite direction. It's like, how much crazier can we make this in terms of like the ideas that we've got? And so we're going to go through them both now. They're quite different and quite interesting. You know, roughly the same depth, and this starts to make the notion of depth kind of blurry, because as you'll see, there's just the architecture is just kind of weird, and totally networks that you will see in your in the model zoos of the deep learning frameworks that you can look at. Now, you don't really see people using them very often, so like no one really uses AlexNet or BGG or Google Net or Inception like kind of for anything anymore. People more use things that look like ResNet and the related networks, the variants of ResNet. And as you know, when we get to ResNet, you'll kind of see why. But it's, you know, some of the concepts that show up here show up here as well, and kind of motivate some of the ideas for the more modern convolutional networks. So VGG. So what's the idea? The idea is, let's make this fairly simple. Let's simplify the ideas here, and let's just see what we can do with these simplified kind of building blocks or modules. So some of the differences. So first of all, there's a couple different variants that you can that are typically in these zoos. Don't get too worried about it. Just one's deeper than the other. But the big differences that you should see right away, and that were pointed out here in the notes, is that instead of having all these different kinds of convolutional layers, meaning like different filter sizes, different strides, you know, and so forth, what you have are these kind of modules of 3x3 stride 1 convolutional layers. So if you look at this, you'll see that there's this kind of module idea to it. So in either one of these VGGs, you start off with a couple of 3x3 convolutional layers, and then a pooling layer. All these pooling layers are the same. 2x2 max pooling with stride 2, right? So the same kind of idea where we just kind of, we take all the 2x2 pools and replace that with a single value, the maximum value from within that pool. ReLU is used throughout, and then we do it again. So there were 64 filters here. Then we do it again, there's 128 filters in a pooling. Then we do it again, there's 256 filters in a pooling, 512, and you can see like this starts to diverge. We start to have a few more, once we're deeper into this network, a few more of these layers with lots of filters and so forth here, and then we have similar fully connected layers at the end. And that's it. So it's just a simplification. It's just like, hey, what we're going to do is we're going to build these things up out of 3x3 convolutional layers, where within each kind of block that the number of filters will be the same, and every time you want to, reduce the size of the spatial extent of the feature maps, we'll just use these pools. Okay, so kind of boring, but you can see kind of where this was coming from, right? It's like people are asking the questions that some of you asked explicitly, and probably a lot of you were asking implicitly, which is like, well, how do I go and choose these architectures? Like, how do I choose how many layers I should have, or how many filters and things like that? And so you can sort of simplify this and say, well, what if we just kind of build it up out of these simple blocks where we're doubling the number of filters each time, and we always use the same size filters. Like, how well can we do? And obviously you could do very well, as seen by the score. Unfortunately, this didn't win in 2014, but it got very close, and did do much better than the previous year's winner. Okay, so let's think about this for a second. Why use smaller filters? What's the point of smaller filters?
They're less like a fully connected layer.
Yeah, they're less like a fully connected layer. Well, what does that mean exactly? Okay, that's fine. Yeah. Yeah. So they're computationally less costly, right? Like the smaller the convolutional size, the less operations there are per filter convolution. So that's important, especially as people were doing the research here and starting to figure out how to make these networks deeper. You needed to have, if you think about if your compute's fixed, which of course there was hardware innovations happening, and we're having, we're able to use more and more memory. But if you imagine that being fixed, if you want to have deeper layers, then you have to pick up memory. Reduce your memory footprint somewhere. So one way to do that is to have fewer parameters, and one way to do that is just to have all your filters be like the smallest possible, without it being 1 by 1 or 2 by 2, which we would never use in convolutions. So yeah, just we have fewer parameters. So to think about this though, are we losing expressivity in some way? So remember we talked about receptive field. Remember what receptive field is? So if you think about a feature map, so the output from one of these convolutional layers, the receptive field for that output is going to be some number of, or it's like some subset of the inputs to that layer. So for a single 3x3 convolutional layer, we look at one of the outputs. What's the size of the receptive field for that?
9.
Yeah, it's 9. It's just 3x3, because it's just the size of the filter. But now do that twice. What's the size of the receptive field?
It's a try 12.
Yeah. So say it in terms of k by k. What's the size of it?
K by k plus k.
Where's the plus k coming from?
From the stride of 1. And so you get the 9 by 9.
Uh-huh.
And then you stride over 1, so that's another 3. Or sorry, 3 by
Yeah,
3.
so let's think about this. So you're on the right track, but just need to change this thinking a little bit. So we go back one layer. We now have we have these 9 values in the 3x3 grid. Now we're saying, okay, if we go back 2 layers for that same fixed output that we're looking at its receptive field 2 layers back. We now take each one of those 9 and we look at what its receptive field is, right? So what does that look like?
But
What?
they overlap, right?
There's overlap, yep. Yep. So each one of those is going to have a 9 by 9, receptive field, but there's going to be overlap. And what does that overlap result in? What's the k by k size?
K minus 1 by k.
No. 5 by 5, right? So just here's the picture. So we go back one layer, we can kind of visualize that because we're saying the filters are 3 by 3. So we know that, to get one of these outputs, we have, we took this filter and did our entry-wise multiplication, summing this like spatially extended dot product with the input. But now if we go back another layer, we're going to have that same kind of like 9 by 9 grid for each of these input values, which are now the output values as we go back one more layer. And so they're each going to have a 3 by 3 grid as a receptive field that overlaps. If you consider what the overlap looks like, what we now have is a 5 by 5 receptive field. And so if you went back one more, what would the size be? 7 by 7, yeah. It's the same kind of idea, right? Take each one of these things, you get a 3 by 3 receptive field for those, and you kind of go through it and notice that there's overlap, and you go down, and so it's 7 by 7. So, having two 3 by 3 convolutional layers, the receptive field going back two of those layers is the same size as having a 5 by 5 convolution. But what you can think of this as is like having factored this 5 by 5 convolution into two 3 by 3 convolutions. And so we can still cover the image with the same size receptive fields as a larger filter. We just need more layers in which to do it. And there's also an advantage there because every time we add a layer, we're adding more expressive power, the ability to integrate lower level features into higher level features. Yeah.
But you also have a ray loop between each filter, right?
We do, that's right. But that doesn't change the receptive field.
Right, but it changes how complicated it can be, like, non-linear.
Yeah. So it's not exactly a factorization. That's one way to think of it. It's like not exactly a factorization of the 5 by 5 into two 3 by 3s. There's like a nonlinear, it's not a linear factorization. There is this nonlinear operation happening. But if we kind of just ignore that detail, the conclusion is the same, that we can have two 3 by 3 convolutional layers. The receptive field of the output of that is the same as one 5 by 5 convolutional layer. So yeah, so like so why is that important? Well, remember what we're trying to do is we're trying to build up low-level features into high-level features, like localized features into integrated high-level features that are integrated across the whole image that will help us perform the task. In this case, a classification task. So 3 by 3 layers on their own are more efficient. They have fewer parameters, and if we can stack them, we don't lose the ability to integrate larger and larger areas of the image into high-level features. So that's maybe kind of obvious as you think about it a little bit more, but nonetheless like a nice design principle in thinking about like what are some simple yet powerful principles for building convolutional networks. Now we already answered this question about like what would this be if there were 3 in a row. You can continue to think about that as well, and also like the number of parameters that are needed is dropping dramatically as we stack these up, which is what we're going for. Okay, so nevertheless, there's still a ton of parameters in these models. These are still big models. So let's look at this. So we're going, that's too bad that we've got the top there. The top's cut off. It says input 22 by or 224 by 224 by 3.
It's on the ceiling.
What's that?
It's
No, it's on the ceiling. Yeah. Anyways, so what you have at each one of these layers is the amount of memory required to store the output from that layer, and then the input, the input to that layer, I guess is what we're thinking about, and then like the number of parameters in our weights. So we have our input, and then we have our each of these convolutional layers. So what you see is as we get deeper and deeper into this network, we see that we have fewer the memory constraints, or the memory requirements are actually going down. Just concentrate on the convolutional layers, right? So we're even though we're having deeper convolutional layers, meaning like we have more filters per layer, because we are reducing the size of the feature maps, that we're getting this kind of quadratic reduction, and so really quickly, the memory footprint for each layer as we go deeper is smaller, which is great. What is happening on the other hand is that as we go deeper, there tends to be more and more parameters that we have to store at that point. So notice how they quickly build up from the 64 3 by 3 by 3 filters that we have in the first layer to take the input, and going to, it's always 3 by 3, but then just as you start to take into account how many filters we have at these depths, you get large, massive numbers of parameters compared to the input, or to the foot of the network. And then what do you notice actually as you move from the convolutional layers to the fully connected layers? No, that's totals. What do you notice? What happens as you go from, say, like this block to this first fully connected layer? Yeah, that's a huge number, right? So we were in like the thousands and tens of thousands, the hundreds of thousands. We got into the millions. That's starting to feel like a lot. But we go to this first fully connected layer. It's really, really expensive, right? It's got over 100 million parameters. This is why, remember, why we're avoiding fully connected network or fully connected layers in the first place. It's just that there's a lot of parameters in that, right? So, by the way, where does this number come from? Well, once we get through all these convolutional layers and then get to this final pooling layer, what we have there is a 7 by 7 by 512 feature map, right? So we've reduced the spatial extent of the feature map down to 7 by 7, and we have this depth of 512. And when we say fully connected, well, we're basically just like turning this thing into one long vector, right? For it to be fully connected. So that vector, what's the size of it? Well, whatever the size of this is here, right? So 7 times 7 times 512. That's the number of entries in that feature map, and then we're connecting all of those to all all 4,096 the output of this layer. So this is just a huge number. And then we have one fully connected layer at the same size, 4096. That requires that many parameters, and then we have to go one more to get us to 1,000, because our task is to classify classify the image amongst 1,000 classes, and so we get that. So so the memory to store the outputs is getting smaller and smaller as we get down, but the number of parameters is increasing, and especially increasing when we do when we get to the fully connected layers. So if you haven't thought about it before, it's pretty important. And what you'll see actually as we go through the history here is that we start to drop these fully connected layers in favor of having deeper, having more convolutional layers, just because of the expense of that. Yeah.
Is there ever any utility in designing a loss function to directly take the output of a convolutional layer and implement that in some way as a distribution?
Yeah. So one thing that we're going to look at is that, like, so it just depends on the task, right? So if you're doing classification, where you from the whole image you're just trying to say, like, which objects are here, you do need to do something that gets you to the class size. So you could skip these fully connected layers here and just go from here to here, right? So instead of it being of this size, instead of multiplying by 4,096, you would have multiplied by 1,000. But there are other tasks, right? So like one of the other tasks that we're about to look at is object localization. So we're going to draw bounding boxes around the image and around the object within the image. And so that has a little bit more to do with like exact pixel placements. And we're going to use the feature maps to do that. There's also this kind of combination of the two, which is semantic segmentation, where we're literally going to classify every single pixel. So every single pixel is going to have, like, we're going to have a loss function for like what is in that, like what class is in that pixel. And so it's going to use the feature maps, as a result. We're going to have to blow them back up to get to the right size, so we're actually doing this kind of pixel classification. But yeah, kind of just depends on the task. But you'll see, simply, because there's so many parameters here in these fully connected layers, the trend will be to cut these out, that they're not needed. And we cut them out because we'll just have deeper and deeper networks that allow us to, to have really rich representations at really small spatial extents for out of the convolutional layers. Yeah.
If you train each layer like one at a time, how does it, or do you just go a full network?
Yeah, you train it end to end, just like in the homework, right? Like you train like a 2-layer network, right? So, or is that the next one? You trained a 1-layer network, 2-layer network in this homework, right? Yeah, right. So it's the same thing. You're back propagating from the loss through all, from up there all the way through to the parameters here at the beginning of the network. So we train it all end to end. You'll see that like the GoogleNet or Inception actually has a slightly different take on that. And when we get there, I'll point it out. Okay, so roughly you need this much. For an image of size 224 by 224 by 3, you need roughly 96 megs to store the feature maps for the forward pass, and there's a total of 138 million parameters. So actually, it's interesting. Like this network actually has a lot of parameters compared to its ability to classify or do other tasks. And you'll see that people aren't using these kinds of things anymore for that reason. There are far more efficient convolutional networks, meaning they have far fewer parameters, but that perform far better than this. And yeah, we'll be talking about them. But anyways, that's some of the stats for this. We talked about this already, where most of the memory is at the beginning of the network, most of the parameters are at the end of the network. Yeah, there are some common names for these things, just referring to kind of the blocks and then the layer within the blocks. I'm going to use this convention kind of all over the place for other convolutional networks as well, because this idea of like building this up from blocks becomes kind of a common pattern. So yeah, so it placed second in the classification, as we already saw that this other network did better than it. These networks were trained in very similar ways to what we described for the AlexNet network. These did not use normalization layers, in particular not the local response normalization. yeah, people were using either one of these. VGG 19 did give a little more, just did give better results, but the memory requirements maybe didn't justify that. As we saw for the AlexNet, the best results were gotten from ensembles of training many of these and then ensembling the results together, right? So like averaging the logits or the softmax likelihoods. Importantly, what people started to do with these networks was to use some of these feature layers for these fully connected layers to be like a lower dimensional representation of the image. And you started seeing that a lot, like these pre-trained networks on Imagenet. You would just pre-train them. You'd send an image. You forward an image through this that you take you to one of these layers here, like this layer here, 4096, and that's just like nice. It's still high dimensional. 4,000 features is a lot, but compared to the size of the input, it's quite small. And then that would then be a representation of that image that would be used in other tasks. And we'll see some examples of that as we go along. But people started using this VGGNet for that because the features were actually quite good. And then it had this notion of like how to properly initialize, which we're going to look at right now. So let's talk about weight initialization. So we're going to talk about something that's known as Xavier Initialization because one of the authors on the paper had the last name Xavier. So weight initialization. So let's just think about making choices for weight initialization. So what happens if we choose a constant? So like for all of our weights, every weight is the same, some constant C. What can we expect about the output for such initialization? Any thoughts? Something like that. I mean, we do have the non-linearities that are happening. Yeah, like if we didn't have non-linearities, you'd have all these kind of linear projections into different size spaces, and so you'd have this kind of, you'd have some kind of like, scaled, rotated, output. We do have the non-linearities, but let's think about a ReLU non-linearity. Like, what does that look like? What's that? Yeah, we're gonna have some zeros in places. The outputs won't all be the same because the inputs will be different, right?
Well, like if you're multiplying a constant matrix by a vector, it's just going to be like summing the vectors for every output.
Yeah, so I think you're saying the same thing that was said over here. Like, if this was just matrix multiplications, one another, like that would be the case. Whatever the output is here, just some scaling of the input. It's going to be like a bunch of matrix multiplications, and then some scaling at C. You could factor those out somehow. So keep thinking about that. So one of the things that is a problem with it is that you are going to get some kind of uniform behavior that we don't want. But keep thinking about that. Let's think about doing some other ideas. So what if we were to, instead of doing something simple like that, we were to randomize the weights? Let's have them be centered at 0, some standard deviation, some small standard deviation. So these are all kind of small, each weight is drawn from a Gaussian centered at 0 with a small standard deviation. So in general, we'd expect these numbers to be small. What would the output of of this network look like? What would you expect to see? On average. Yeah. So things ought to be probably small because you're multiplying by small values. What else?
Predicted outputs should just be in a random distribution. Like there should be a pattern.
Yeah, like so. What would be like the average of that distribution?
I guess 1 over the number of classes that
Yeah, when you get to this, when you get to the softmax, yeah. So like, you would expect there to be something like, yeah, you're getting to something important, like the out. So each of the outputs in your output layer is going to be drawn from a similar distribution, and so meaning that they'd all have kind of the same expectations. So if we now do a softmax, we'd expect that we'd expect that distribution over the classes to be uniform. That's true. But what's this expected value for the output?
0.
Yeah, yeah. So it'd be 0, because you're like, it does depend on it depends on the inputs. But let's say that we like also centered the inputs somehow. Like we, instead of just putting in the inputs, like we did some kind of normalization of the inputs where they're also centered about. They're centered about 0. Maybe we scale them as well. But the point is that you're taking all these centered inputs and you're multiplying them by things that that have as much likelihood of like multiplying by a small positive number as by a small negative number, and they're going to start to cancel out. And we'd expect to see very small numbers on the other end with expectation 0. There's a bit of nuance depending on the activations, but yeah, that's what we expect. What's the problem with that? Yeah.
The small values are not counted on slope, right?
Yeah. So think about these weights are these weights are the things that are giving us like the size of our gradients, and from one layer, like the gradients of the layer of a downstream layer are depending on the size of the upstream layer, and if you think about multiplying by matrices with small values, the eigenvalues are going to be small. That as we iterate that process, we're going to get smaller and smaller values because these eigenvalues will also be smaller. So things are going to be small, and our gradients in general are going to be small. So learning here is going to be a problem. So if the networks are small, meaning like they're not deep, then this might be okay. But as they get deeper and deeper, think about each one of those being like multiplying by another one of these matrices with small entries. We're gonna it's another way of kind of like dampening that signal or like squashing it out. So we don't want to do that. That's going to be a problem for us. We want there to be some gradient signal coming out of these networks. So what are some other ideas? Well, before we do that, let's think about let's think about this idea initializing in the way that we just did. So this is what would happen. Yeah. So if we had standardized our input, this would be this is like the statistic of the entries in the feature map for each layer. So they are centered at 0, and they start off having some kind of larger standard deviation, but as we iterate these with the same sized inputs, same sized weights or distributed weights, that we're going to keep squashing that signal down. So we've got nothing. And really, it's not the signal itself is not the problem. It's that there's no separation between these things. There's no gradient there. There's nothing to learn from. So that's our problem. Okay, so how do we overcome that? Thoughts? What are some things we could do? I believe we already mentioned it one time. Like
just widen the distribution. So not
you could. You could widen it. What's that?
Center not at 0.
Okay, good. So let's talk about this. So you could make them larger. So that, what effect would that have? It would basically just kind of prolong this effect, right? You'd still get this kind of the squashing, you know, as you get deeper and deeper into the network, but it would take longer. So, you know, maybe there's a balance between the size of those and the depth of the network. In general, though, we want to get to a technique that doesn't require us to think about like how deep the network is to tune that. Okay, so the other idea was to maybe have it not be centered at 0. Is that what you said?
Centered at 1 or something.
Okay. What would that do?
If it's generally above 1, then you're not going to go small.
Yeah. So, oh, I forgot we have this in here. This actually addresses something that you were getting at. Sorry, we're gonna get to this in just a second. So this is interesting. So we didn't look at I didn't get too deep into this, but like in this toy example right here, we're using a tanh activation, not a ReLU in between here. And so what happens? So yes, you would prolong, but if you have these ReLUs, but if you have a tanh, if this becomes really large, what you see is that you kind of get this bifurcation in terms of what this like dynamical process of iterating the maps looks like, and it pushes out to the extreme values of the activations to -1 and 1. That's also really undesirable because while there is differences between the stuff here and here, you still have the same problems, you know, within each of these modes of there being no difference between those.
Don't the inputs go beyond 1? How are we keeping all of that?
Well, it's tanh, so the activations are tanh. I failed to point that out, but they're tanh. So our activations are going to be between -1 and 1, right? So the linear layer, it can be whatever value you want, but then you apply that activation, and they get squashed between -1 and 1. So this is what would happen in that case if you use the larger, and if we stick with like ReLUs, then we'll just get the squashing down to 0 eventually. Okay, so what are some other ideas? Well, there was this idea of maybe center it someplace else. That is a good idea. We'll get to that in a second. What the Xavier initialization does is to kind of do this thing of like making the distribution wider to accommodate, but doing this from layer to layer, so that it sort of takes care of itself. So the idea here is that when we our weight matrix is of a size, the value, so the numbers here, or the variables that are representing our numbers, the dimensions of our weight matrix, are this fan in and fan out, which is like the input size and the output size, right? So we have a matrix of fan in times fan out dimensions. So if you look at this paper, you can kind of look through this, and they do this analysis where if you just think about this as factorizations, and you normalize the weights by dividing by the square root of the size of the input, that you should expect to, in the linear case, sort of preserve the size of the inputs, or the distribution, like the standard deviation of the output, the distribution of the entries of the feature map at each layer. And like the reason for that is something along the lines of, if we have a lot of, let's see, what's the right way to think about this? If we have a lot of dimensions coming in to one of these layers, and we divide by the square root, we're scaling by we're sort of undoing what we would expect from the central limit theorem. Right, so the central limit theorem is something that says that if we're sampling from any distribution and we're looking at averages of larger and larger numbers of that sample, we should expect that actually to to converge to the average of the distribution, where the standard deviation of that distribution is getting smaller and smaller according to a square root law. So this is sort of like following the same arguments there, that since we expect that in this linear case to be getting smaller and smaller at that rate, we sort of undo that with this particular normalization at each layer. So that's kind of where that comes from. We're not going to get any deeper into that. And it sort of works. At least it worked for the depth of the VGG network, so like 16 to 19, like a 20-ish layer level. This actually still has problems if this gets too deep, but it worked out pretty well there. And it was thought that, notice that this paper was actually done before 2012, right? So the AlexNet paper. So the fact that the AlexNet group didn't use it is interesting, but it was used here mainly because when they were getting to these deeper and deeper layers, they were observing squashing of this signal as a result. So, anyways, this got them out of it and allowed them to have deeper networks, which of course is like the story of progress being made here in deep learning. If you want to summarize it, it's deeper. How do you train deeper and deeper networks? So, anyways, that's why that is like that. Questions on that? Yeah, so VGG, they submitted a whole bunch of, an ensemble of a whole bunch of different ways of putting these modules together. And they did use similar training techniques with respect to data augmentation and such, and anyways, they got to the 6.8. So very, very simple construction, a little bit of trickery in terms of needing, so no normalization layers. That's actually really interesting because normalization layers, we have them all, they are a rule now in convolutional networks, from ResNets on. But they sort of got away from needing that by some of the trickery, in particular, how they initialized the network. However, there was a network that did slightly better, and it's this GoogleNet. It's a play on the fact that this LayNet was the first successful neural network, and that was a play on the name of the creator of that, Jan LeCun, and he had come to Microsoft by that point, sorry, not Microsoft. This was done at Google, and anyways, this was just he was at Microsoft at this point, but this was just sort of like a call out to saying hey, here's some cool convolutional networks, but we're doing this at Google. Anyways, so this ended up becoming Inception, called Inception Net, and literally, it's a play on the popular movie at the time. Hopefully you've seen this. It's quite a mind bender. And this network is totally a mind bender. So it has the same spirit as a VGG in the sense that we want to build these up out of similar blocks, just that we repeat over and over again. However, these blocks are totally weird. They're totally kind of unexpected. And what they are, we're going to go through now. We're going to go through this Inception module. So before we dive deep into this, let's just talk a little bit about what this looks like. So this network has a couple of standard convolutional layers at first, and then you have a bunch of these inception modules that we'll talk about, and then you have a single fully connected layer to get you to the correct score, and, you know, softmax, and you're done in your loss function. So, okay, so what does this mean? Well, this is quite efficient for a couple of reasons. We got rid of the fully connected layers, so we don't have all those parameters in those final layers. In fact, we only have 5 million parameters in this 22-layer network, although like how you count the layers is a little bit weird here. And so much smaller Analyx Net, much smaller than VGG, 16 or 19, and it's actually the winner, right? So how did they do that? They have far less parameters. You would think this network has far less capacity to learn to do a task like classifying Imagenet, and yet they did it, and that's because they build in this kind of crazy inductive bias through these modules. Notice too, I think we call this out a little bit later, but you might be wondering as you look at this, there's like these side branches here that kind of look like the final head of the network up there. And literally, it is. This is like a, because this network was so deep, at least for the time, they had a hard time propagating the loss from the head of the network all the way to the beginning of the network. So they got around that in a couple ways, and one was to just basically add the loss at add branches to have a contribution to the loss earlier in the network. So basically, the output from this third Inception module has its own head that has a loss function on it, and then go up 3 more Inception modules, and it has another head with that has a loss function. So basically, when this thing is optimized, it has 3 loss terms from these different parts of the network that are, you know, combined together. And when we backpropagate through that full loss, which means that any weights here closer to the beginning of our network, they are receiving signal not just from kind of how we've seen, up to this point, from the loss from the head of the network, but from these other heads as well. And the point of this is that, like, the loss here, the signal from this loss is much stronger because it's closer to these weights than, say, that one, which was being attenuated as we backpropagate. So, kind of clever. Future iterations of this get away from this by doing some normalizations, but yeah, sort of interesting. All right, so let's get into these modules. What is going on here? The idea here is, the idea of these modules is to have sort of like a network in network. Like, each one of these modules is going to do some operations that will extract certain types of features at certain scales, and all of that will be concatenated together to be the output of this layer. So what does this look like? Okay, so naive inception layer, or naive inception module. So if you're having a hard time choosing the size of your filter for your convolutional layer, why not just use them all, right? And that's exactly what happens here. So naively, we go, okay, well, we don't know if we want a 1 by 1 or a 3 by 3 or 5 by 5. I guess you could go to 7 by 7, but literally, that starts to be a very costly operation. So they just use them all. And not only that, hey, why not just throw a max pooling in there as well? Because that's another way to extract information from these. And that's literally what happens. Is we have, we choose a number of filters that'll be 1 by 1, then 3 by 3, and 5 by 5, and we're going to learn those. We'll also have this pooling, which won't have a learnable layer, but it will contribute to the output from this module. And all we're going to do is we're going to concatenate these, the outputs of these together. To be able to do that, we need to make sure that we maintain the spatial extent of each of these of each of these operations. So, you know, in convolutions we do that by padding, as we've already discussed. You know, for 1 by 1 we don't have to worry about it, but 3 by 3 we add, you know, one padding layer around the image, and for 5 by 5 we do 2. And then this pooling operation, we just need to make sure that to maintain that we're striding by 1, so that we maintain that spatial extent. And if you can do that, then you can just concatenate all these feature maps from each one of these together to get one really like much deeper feature map at the end, but all, you know, all the same spatial extent. And that becomes the input to the next layer. Okay, so this is called naive. And why is it naive? Well, what might be problematic about this? Besides it just being kind of weird. Like, what have we been talking about this whole time about BGG and the 3 by 3 convolutions? Yeah, so we're trying to get to less parameters so that we can have deeper networks for a fixed like memory budget, right? But this is just saying, like, I don't want to choose, I'll just use them all. So we could have, so there's a couple of choices you can make there. You could have there be fewer filters per convolutional layer here. Or you could sort of deal with that in a different way. And so they deal with that in a different way. Yeah, sorry, I asked the question without going to the slide. So, you know, if we were to think about this, if we use these numbers where we have 1 by 1, we have 128 1 by 1 filters, 192 3 by 3, 96 5 by 5. Why those numbers? Well, they're the numbers that are in a typical Inception module. If our input's looking like 28 by 28 by 256, if we go through each one of these, what's the output size of these layers? Well, what is it going to be for this right here? So 1 by 1, 128 filters.
What is the point of a 1 by
1
1?
by 1 is just going to do a dot product down the depth. So it's not really doing that kind of like local integration, except through the filters.
Okay.
Yep. So it's still doing something, but only 1 by 1. So what's the output of that look like? Perfect. 28 by 28 by 128. What about for the next one? What about for 3 by 3 and 192? We have padding of 1. 28 by 28 by 192. 28 by 28 by 96, and then we maintain. Remember, we're doing pooling here. We're just gonna have stride 1. We'll do padding as well to make this work. So we maintain 28 by 28, but the depth of this will be the same depth as the input. So this is the output from these layers, from each of these layers that are running in parallel. And we're going to concatenate them all. So we get a 28 by 28 by 128 plus 192 plus 96 plus 256. So that, add those all together, that's 672. And how many convolutional operations do we have to do to get to that? You know, here's all the multiplication of all those. You know, almost 1 billion operations just for this module. So that's a lot. As we already saw, you know, kind of comparing to like a BGG, just what was happening at each layer. So that's kind of problematic. Like, yes, this is kind of cool idea, but like to implement this for real, you're not going to have very many of these modules. You're gonna use up your computation budget. You're going to use up memory and all that really quickly.
Where did the 256 come from?
From the 3 by 3 pool.
Oh, that's from the, no, I was talking about in the first line on the right. That's from the depth. Yeah, 1 by 1.
Yeah, because there's that many. This is the size of the filter, or this is the depth of the input. Yeah. Okay, so what can we do to get around that? So, so this is really important. This is something that inspires what you'll see in ResNets in the way that those get built up. but the idea here is, like, what's causing all this to be, you know, to like, what is the problem? The problem is that we're doing all these convolutions with so many filters. The depths, you know, the operations grow with the you know, linearly with the depth. So we can do something about that. We can change the depth. And this idea of what will be called bottlenecking is a really important concept in the design of neural networks, of efficient neural networks. So we talked about one by one before. There was just a question. You know, literally, think of it as like, you know, it's like a dot product for each of the depths with a single vector filter. You're just doing it for every single one of the inputs in the every single one of the column inputs or entries in your input. Is there a question?
So when you can do it with a 3 by 3 and 32 filters, you still get 32 depth out, right?
That's right. But instead of doing, but now you don't have the 3 times 3 operations per filter. It's just one, right? Or the 5 by 5, which is 25, right? So like, there's just this one. So like that reduction of that kind of like quadratic cost, you know, saves us quite a bit when, yeah. So we put that together. So we have like a cheap operation to reduce the number of filters, and then we do convolutions 3 by 3 and 5 by 5 with fewer, with less depth, which in general is like reducing the capacity. But the fact that we kind of like learned that compression from greater depth to less depth is like, you know, it at least has there's some additional parameters. It's again thinking of it as a kind of a factorization of those operations. But yeah, the idea here in the not naive, the actual modules that get used, is that before we go into the expensive 3 by 3 and 5 by 5 convolutions, we actually do 1 by 1 convolutions to reduce the depth of the feature maps, do these more expensive ones, and then concatenate. Okay? And so this is a way of being able to control the computational cost of this whole module. Now, it kind of seems weird at first when you just look at it like this, because it feels like we're just adding more computation, right? There's like additional layers. But the whole point of these is to reduce the depth so that these are less expensive. So you can kind of, again, think of like the deeper 3 by 3 and 5 by 5 layers. You know, think of those as being factorized into these two operations right here. Oh yeah, and then I failed to point this one out. Because this preserves the depth of the input, we also may be interested in compressing that as well, so that we have fewer operations, and that's what we do. We have a 1 by 1 convolution on the other side of the max pooling to reduce the depth there. So if we do that using these numbers, using 64 1 by 1 filters before we enter here, and then 64 1 by 1 filters after this 3 by 3 pool, then we go from having, you know, 800 plus million ops to 358 million ops. So, you know, like a reduction of like 2.5 times or something like that. And yet we're getting some of the same expressivity, which is really, really important here. So that's what those look like. We're going to stack those up one after another. I kind of already pointed this out, but there's this like beginning part that's just some convolutions and pools, like 2 layers here, with well, there's three layers. So a convolution, a max pooling, convolution, to max pooling, and then we get into these stacked Inception modules. Then we have our classifier output, and then you have these funny things here at the end. Oh yeah, so I already pointed this out, but notice that there's only 1 fully connected layer here, not 3. And then but then you have these ones here for the first Inception Net or Google Net. There are two fully connected layers there, which I'm not really sure why there are two fully connected layers. I never tried to pull one out and see how much worse it is or whatever. But that is how they designed it. So you're getting signal. You're getting signal from each one of these. So if your weight's here, you're only getting signal from this loss. If your weight's here, you're getting signal from this loss and this loss. And if your weight's here or before, you're getting signal from all the losses. Okay. So there you go. That's Inception Net. So we have roughly 10 minutes left. So that group at Google started iterating on these ideas, and there became a lot of different versions of Inception Net. So Google Net is the name for Inception V1, version 1. But then after that, you have Inception V2 and V3 and so forth. And importantly, in these subsequent Inception Nets, this group introduced probably the most important normalization layer for convolutional networks and for other networks as well, called batch normalization. And this really revolutionizes their ability to have very deep layers. This and the residual connection, which we'll learn about in ResNets. So this gets used in ResNets basically at every single layer. This is used at every single layer in the Inception. But it's this idea of batch normalization. So what is batch normalization? So the idea is the following. So we've talked about this already. So think about the output. So let's say we're using ReLU activations, and we think about the output from one of these layers. So a linear convolution layer, and then this ReLU output, this ReLU activation. So all of our values now in the output tensor are non-negative. So they're either 0 or they're positive. Okay? So that means that our distribution is it's got some non-zero mean, as long as there's at least one non-zero output in that feature map. And it could be any kind of wild distribution at all. It could have all kinds of statistics. That mean could be anything, and the standard deviation or the variance could be anything. Higher order moments could be anything. And maybe that doesn't seem like such a big deal, but if you think about it, if you think about our networks in layers, what you really want you're going to make it much easier for each layer to learn if the distribution of the input is roughly the same at every batch. Now you can't really make it the same, obviously, the data could be quite different, but if you can sort of make it so that the statistics of each the distribution, some of the statistics of the distribution of outputs in your feature map is roughly the same each time, then that layer has a much better chance of learning real signal, because instead of having to learn to normalize it on its own, or do that kind of pick out the differences from averages or from means and from the scalings on the features, if that's already done prior to that feature map being inputted into the next layer, then that layer doesn't have to worry about that. That layer can just focus on deviations from the expected statistics. And that's what normalization layers are for, and in particular what batch normalization does. So batch normalization literally takes your batch and it computes the mean. So we have the output from a previous layer. It computes for that whole batch the means, the mean across that batch, the batch level average. And for images, you think about this at for each channel, for instance, you know, for the depth of the feature map at like each layer of depth in that feature map. And then we compute standard deviation, so the square root of the variance, again for each, you know, depth there. And we normalize we normalize the output for each of those entries by the batch level statistics, or we standardize by the batch level statistics. So we subtract by that average, and we divide by those standard deviations. So now all of a sudden, each of these features, before it, at the batch level, before it goes into the next layer, has mean 0 for that whole batch, and then has, basically each feature has standard deviation of 1. So what we're doing is we're shifting the distribution around just through these simple arithmetic operations, so that the distribution of the outputs from that layer now sort of just look more, you know, like they're, what am I trying to say? They have distributionally statistics that the network can sort of rely on, the next part of the next layer in the network can rely on when it's now going to learn from those. And it makes it much, much easier for the network to learn as a result. So very simply, you take your batch, you take all of the outputs, that feature map, you compute means across the depths, you compute standard deviations across the depths, and then you standardize each of the feature maps for each of those inputs by those statistics, and that now becomes the input to the next layer. And this helps tremendously. And it's called batch normalization mainly because you're doing this at the batch level, right? Like you're computing batch level statistics and standardizing by those. Okay. Any thoughts on whether or not that's good or bad? Like, is this going to achieve the idea, this idea that we're gonna distributionally kind of make each input the same, no matter the batch? Yeah.
So I have a question.
Yeah.
Say for each depth of the input, does that mean like for an image with 3 color channels, you're gonna
Do this per channel.
It's per channel, not like per pixel?
No. Yeah. There are. I mean, you can imagine standardization being like that, but this doesn't do it that way. This does it, you know, per channel, like per depth.
Per channel, per pixel.
Yeah. Not per pixel, across the whole channel per batch. So
it would be like the average of all of the reds in all of the pixels in all of the images in a batch.
Oh, I see what you're saying. I see what you're saying. Yeah. So
It's the average.
so it is per pixel. Sorry. Yeah, I see what you're saying. Yeah, I was misunderstanding. It is per pixel. Like you're going to subtract this literally from that. Now you can do this at different levels of aggregation, but this is like the standard way of inputting that would be per entry in that feature map.
Right.
Yeah.
So if you have like a representation of an image that's like 3-dimensional, your average, the output of the average function is also going to be 3-dimensional.
Right. That's right. Okay.
So does that mean that after normalization everything is between -1 and 1?
No, because like you could still have really, really large values, but what it does mean is that all those features are centered at 0. Right? So you're going to have, if there was any difference at all, there's going to be some that are negative and some that are positive within that batch after transformation. That does not mean that they're going to be like standard normals, but they are going to be centered at 0, at least for that batch, like that subset of your data. And also each of the features will be standardized, meaning that they'll have standard deviation of 1, again, for just that batch. So it could be like a totally weird distribution. I could have like really wild kind of skew to it, right? So it's not like symmetric about 0 or something like that. Could be really weird, but at least we've changed the distribution of this the feature map for this batch such that we have 0 means and we have unit standard deviations. And this makes it much easier for the networks to learn, or for each subsequent layer to learn from the outputs of the previous layer.
So each pixel is not a pixel anymore. It's like how far is from the average pixel at.
Yeah, I mean that's the way to think about it, right? These are like z-scores. We sometimes call these, right? When we standardize like this, and it's like whatever is the characteristic standard deviation. We now transform that so that 0 is kind of the standard size. We have both positive and negative values, and then when we think about how much variance there should be in each of those features, the standard deviation should be 1. Yeah. Yep. Okay, so yeah, so there's more of the operation. So where do you put these? We're about to run out of time. So when this is introduced, these are put after the activations and before the next linear layer. So this is showing this as if we have some fully connected layers and the activations tangent. These could be convolutional layers and the activation is very minimal. This is like when this was introduced, this was a typical way to do this. Actually, this is like the recommended way that this gets done has changed, where like the batch normalization should maybe come first. But again, this is all empirical. The idea is that you wanted to standardize the non-linearities before they go into the next linear layer. So one last important thing about a batch normalization is that while you do want to do this normalization and make it easier for the next layer to learn, what was found to be useful was to not just input that, but to allow there to be a couple of learnable parameters within this batch normalization. And so there's a simple kind of affine transformation where we scale these transform values and then shift them. So scale them by a gamma and shift them by beta. So if it is truly advantageous for this to just be the batches have 0 mean and standard deviation of 1, then this will just be a 1. This will just be learned to be a 1, and this to be a 0. But if for some reason there's some advantage for this, for there to be some learned scaling here and some learned shift here, then we're allowing that to be learned. In fact, when you initialize these things, you typically initialize these to be 1s and 0s, just kind of under that expectation. But if you allow this to be learned as well, then it may be that other parameters besides 1 and 0 are useful. And in fact, it turns out they typically are. Still, you're giving the input. So the statistics of the input to the next layer are going to be preserved. It's just they're no longer going to be like 0 mean unit standard deviation. They'll be possibly scaled and shifted, but that might be useful for the next layer. And you can imagine how this is with like ReLUs. If you need to have a little bit of bias to move you to have possibly more of the activations to be preserved through the layer, then maybe having a bias, a non-zero bias would be useful for that reason.
So if you're going to do this at every layer, does that require that you calculate like in forward pass, do a 1-layer forward pass for every single element of the batch, and then you calculate the means after that layer and do your normalization?
Yeah, like this is just like another computation. So you forward it through like say like through the activation, and then the next operation is to do this, is to do this center scaling, and then to do this possible shifting. And when backpropagate, we have to backpropagate through these parameters as well because they're learnable. I don't know, is that your question? Sorry.
Yeah, I think so. I mean, I've had like an image, I guess, of some like batch training where like you get one image and like goes the whole thing and back.
Oh, I see. Yeah. Okay. This is a really excellent point. We are mixing right now. So this operation makes the output depend on the whole batch. I see what your question is now. And yes, that is the case. So we're done with time. What we need to do is talk about one last piece of here before we're done. I can't remember where we have this here. Oh yeah, it's right here. So the question is, whenever you're doing things like this, there's always the difference between what you do at training time and what you do at test time. So at training time, you are learning, like, you know, you're each of these batches, you're doing the standardization. You might be doing the scaling and shifting by these parameters gamma and beta. But at test time, you don't want the output to depend on the batch, right? Because like that would be kind of weird, right? Like that means that, you know, your choice of batch would change possibly the class you might assign to this thing, right? And you don't want to do that. So what do you do in that case? Well, in that case, you are going to take at test time, you are going to use the learned gamma and beta in this transformation, in this layer. But what are you going to do about the statistics, about the mean and the standard deviations that you've been computing per batch? And the thing that is done here is that you keep you keep a running average of those statistics, the batch means and the batch standard deviations, and usually an exponential running average. And the idea of that is that after training, you know, over your whole data set so many times, that ought to represent be close to the actual average for the whole data set, the whole training set. And so the idea is that you're using, you know, the means and the standard deviations from the whole training set. But instead of computing that for, you know, a very large data set, you're just basically keeping like an exponential moving average of those from iteration to iteration, and then you use that at test time. And that's really, really important, right? So you get away from, you know, the classification, like the performance of the task on the batch that you chose to compute to forward that image with. So great question. Okay, we'll stop there. Sorry to go over a little bit. Appreciate you sticking around, and happy to answer questions.